Welcome to The Explainer. Today, we're cracking open a Nobel Prize-winning paper from 1939 that gave humanity a revolutionary new way to listen in on the deepest secrets of the atom.
Okay, let's just dive right into this. Right from the get-go, the authors made it super clear that this wasn't just about measuring some tiny number. They knew that this one property, the magnetic moment, was a critical key to unlocking the two biggest questions in nuclear physics. What holds the nucleus together and what does it actually look like?
So before this experiment, trying to accurately measure the magnetic properties of a nucleus was, well, incredibly challenging. But getting it right, that was absolutely essential for physics to move forward.
Because physicists understood something really fundamental. The biggest discoveries often hide in the smallest details. A tiny, subtle difference between what you measure and what the theories predict, well, that could be a giant flashing sign pointing towards entirely new physics, hidden deep inside the atom's core.
The problem was, the existing tools were like trying to measure a single grain of sand with a big, clumsy yardstick. They were just too blunt. To test all the exciting new theories that were popping up about the nucleus, scientists desperately needed a new, much sharper instrument.
So this is where it gets really clever. RABI's team came up with this brilliantly ingenious system to isolate and basically talk to a single nucleus and then measure its response with just incredible accuracy.
They designed this beautiful piece of equipment. It all starts with an oven that cooks up a beam of molecules. That beam then gets fired through a series of 3 powerful magnets, and each one has a very specific job to do before the molecules finally hit a detector at the end of the line.
So let's follow a molecule on its journey, okay? First, magnet A has this uneven magnetic field that basically shoves the molecules off their straight path. Then magnet B has an exactly opposite uneven field, which acts like a perfect lens, pushing them right back on course. So if nothing changes along the way, the molecules get beautifully refocused and bingo, they hit the detector.
But right there, in the middle of that journey, inside magnet C, that is where the real magic happens. This is where they make the nucleus spill its secrets.
You see, every nucleus, when it's sitting in a magnetic field, it wobbles. It precesses, just like a tiny spinning top. And it does this at a very specific, very natural frequency called the Larmor frequency. Think of it like a unique fingerprint for that type of nucleus.
So to mess with that wobble, the team basically stuck a tiny radio transmitter right in the middle of the C magnet. It sends out this oscillating field that shouts a specific radio frequency at the molecules as they fly on past.
And that brings us to the key question of the entire experiment. This is the whole ballgame. What happens if you manage to perfectly tune your little radio transmitter to the nucleus's own private frequency?
And this lays out the core concept so brilliantly. If the radio frequency is wrong, the nucleus just ignores it. The molecule stays on its path and it smacks right into the detector. No problem. But if the frequency is exactly right, the nucleus absorbs that energy and physically flips its orientation. That flip means magnet B can't refocus it anymore, and the molecule gets thrown completely off course, missing the detector entirely.
So the signal they were looking for wasn't a sound or a flash of light. Get this, it was the absence of a signal. A sudden drop in the number of molecules hitting the detector was their gotcha moment, proof that they'd found the right frequency and made the nuclei flip.
Okay, but how could they possibly scan through millions of frequencies to find that one perfect note? It sounds like finding a needle in a cosmic haystack, right? Well, they had a really clever workaround. Instead of fiddling with the radio dial, they kept it constant. And then they slowly and very precisely changed the strength of the main magnetic field in magnet C. See, since the Larmor frequency depends on the field, changing the field is just another way to find that perfect point where they match up.
And this is exactly what they saw. They'd watch the detector reading as they swept the magnetic field. The beam intensity would be high and steady, and then suddenly, at one very specific field strength, it would just take a sharp nosedive. That was it. That was the resonance minimum they were looking for.
That dip? That was the eureka moment. It was the smoking gun. It was the undeniable proof that at that precise combination of frequency and field strength, the nuclei were soaking up energy and flipping their quantum state. And from the exact location of that dip, that specific frequency and field strength, they could calculate the nuclear magnetic moment with a level of precision that was, frankly, just impossible before this.
This new method wasn't just confirming what people already knew. No way. This was a brand new tool that immediately started to challenge existing measurements and refine our entire understanding of the atom. And here they are, the landmark results from their 1939 paper. You can see the magnetic moments for 3 different nuclei, lithium-6, lithium-7, and fluorine-19, all measured with just stunning, stunning accuracy.
And remember that whole problem of precision? Well, get this. Their new value for the ratio of the lithium moments was a full 2% different from the best prior results. In the world of nuclear physics, that isn't a small correction. It's a huge chasm. It just goes to show how powerful and how necessary this new technique really was.
The legacy of this one experiment is just immense. This magnetic resonance method became a new gold standard. It provided theorists with the hard, precise data they desperately needed to build better models of the atom. And its core principle? That's the very foundation of the MRI machines that save lives in hospitals today. For this work, RABI was awarded the Nobel Prize in Physics in 1944.
Ultimately, the genius of this experiment was turning an invisible, abstract property of the atom into a simple, measurable signal, a dip on a chart. And in doing so, they didn't just find an answer. They gave science an entirely new way to ask questions, opening up whole new fields of discovery.